Hello everyone, welcome to Wi-Fi Learn. In this video, we can see about input and output resistance in a passive network or input and output resistance in a network. In a single source network, that is, if a network contains a single source, assume this as a network and it has a single source of only V1 and the current flowing through this network is I1. In such single source network, the input or a driving point resistance is often calculated where the driving voltage has been designated as where the driving voltage has been designated, that is, this current derived by this voltage only. Since only V1 is a source, so that I1 can be given by V1 in terms of resistance of a passive network. In the combinations of passive network, there are number of resistance may be connected in meshes. Those meshes can be of any number. The input current driven by this source voltage can be given by I1 is equal to V1 of del 11 divided by del R, where del R is a symmetrical resistance matrix or resistance symmetric matrix or symmetrical resistance matrix. This symmetrical resistance matrix is formed by the branches of resistance which has been connected in this network. But del 1 or del 1 can be given by removing the first column of the symmetrical resistance matrix and replacing with that voltage source or by voltage source. This is a resistance matrix of the particular first measure corresponding resistance matrix of this node. Okay. We all know, according to Ohm's law, resistance can be given by V1 divided by I1. So, if V1 divided by I1, your resistance can be given by del R divided by del 11. Right? On doing mathematical manipulations, you will get the resistance value as del R divided by del 1, where del R is a symmetrical resistance matrix and del 11 is the resistance corresponding to that mesh. So, this is the input or driving resistance for a single source network. Since the current has been driven only through this voltage, your current equation can be given by this equation. From this equation, after manipulation, your resistance value is del R divided by del 11. In a circuit, or if a voltage source applied to a passive network, assume this is VR, you are applying to a passive network and the IR is a current drawn in the input side, and this passive network results in the voltage between all the nodes in the network. If there are number of nodes and there are number of nodal voltages and an external resistance connected between the two nodes, that is, if you are connecting the external resistance in the output side, the current drawn by the two nodes will be dependent on the voltage and the resistance that has been connected to those nodes. This is due to the voltage across the output resistance. If you are connecting the external output resistance, the current drawn by the resistance depending upon the voltage across the resistance which you have been connected. So, our output can be given by V open circuited voltage divided by short circuit current. VOC is the open circuit voltage. If you open the circuit and find out the voltage, that is the open circuit voltage, and if you short and find the number of value of the current which is flowing, that is a short circuit current. This resistance will be using in the, this resistance value would be used in the Thevenin and Norton theorem. Thevenin and Norton theorem to find out the output resistance which has been connected to the passive network, to find out the current drawn by the nodes which you are connecting in the external end. Okay. To find out the current drawn by the load which you are connecting after the passive network, those current drawn by the resistant is dependent on the voltage source between the two nodes where you are connecting the load or where you are connecting the external resistor. This R output or external resistance value is used in the Thevenin and Norton theorem, and this driving resistance are used in calculating the nodal voltages by the method of using matrices and determinants. Node voltages can be calculated by using those 3 steps, but for solving we can use either algebraic method or this matrices and determinants also, that is by using Cramer's rule. In this circuit we can find the number of principal nodes. There are 3 principal nodes. This is node 1, node 2 and node 3. I am taking one of the node has to be taken as a reference. So let's take the third node as a reference ground. So 3 nodes are there, one node has been taken into ground. So we have to write the equation for the remaining 2 nodes. So the number of equation will be reduced 3 to 2. So we can draw the matrix. We will get a 2 cross 2 matrix since there are since the number of nodes is 2. We will get a 2 cross 2 matrix and the equation is also 2. So the 2 cross 2 matrix requires elements of 4. The first element will be the self element and second will be the common element, and this resistance matrix is also a symmetrical matrix. Okay, this resistance matrix is also a symmetrical matrix, and this equation is written in the form of I is equal to V by R. I is equal to V by R. You are going to write the nodal equation in terms of KCL, right? So the equation would be of first is the self resistance of the first node. The resistance which is connected to the first node are RA, RB and RC. We have to write the resistance in the reverse manner. So 1 by RA plus 1 by RB plus 1 by RC. And this is the resistance which is common to first and the second node, that is RC. We have to write in the negative value 1 by RC. 1 by RC. If you are considering this node, the current may be leaving this side. If you are considering this node, your current may be leaving this side. So we have to change the sign of the resistance. So minus 1 by RC. So resistance is a symmetrical matrix. So minus 1 by RC. And the last element is a resistance which is connected to the second node. That is RC, RD and RE. So 1 by RC plus 1 by RD plus 1 by RE, which is equal to nodal voltages V1 and V2. Okay. And the current value through this V1 is VA by RA, your first current, right? VA by RA. And through this, your current value is VB by RD. This is the current which is drawn or driven by VA, and this is the current which is driven by VB, I1 and I2. Okay, you are going to find these currents. In general, you can write this as 1 by R11, 1 by R12, 1 by R21, 1 by R22 divided by V1, V2, which is equal to I1, I2. This is the general format for the matrices and determinants for a nodal voltages. Your R11, R22 are the sum of the reciprocals of the resistance which is connected in the node 1 and 2. Your R12 and R21 are the sum of the resistance which is connected between those two nodes taken in negative sign. You have to take that in negative sign. 1 by R21. You have to take that in negative sign. Okay. These I1 and I2 are the driving currents, that is derived by the two sources that has been connected. Both are taken as positive. These driving currents are taken as positive because both the currents are driven into the node. If the current is driven into the node, you have to take it as positive. If the current is driven away from the node, you have to take the current as negative. This is similar to the matrix formation which we have discussed already in the mesh analysis. There the resistance are taken in the straight manner, but here the resistance are taken in the reciprocal manner. That's it. The KVL equations is formed according to V is equal to IR in matrix, but in the case of nodal voltages, you are finding the matrix in I is equal to V by R. V by R is equal to I. So this can be further reduced as in terms of 1 by R is reciprocal of resistance is a conductance value. So you can write G11, G12 minus G12 minus G21, G22 into V1, V2 which is equal to I1 and I2. As we all know, I is equal to V by R, I is equal to V into G, where G is the conductance measured in Siemens. G is a conductance measured in Siemens. Since conductance is opposite of resistance, conductance conducts a flow of current. This equation is also valid. See the problem we can solve by using a matrices and determinants method, just by using Cramer's rule. For the network shown in the figure, find I through the 10 ohms resistor. The current flowing through 10 ohms resistor. Here the number of principal nodes are 1, 2 and 3 here. I am taking this third node as a reference node, that is grounded. So you will write the equations for 2 nodes. The number of equations would be 2. So the matrix can be formed also 2 cross 2 matrix which has 4 elements. If you write the matrix format, the first element would be of self element, that is connected to the node 1. The element connected to the node 1 are 5 and 10. So 1 by 5 plus 1 by 10. And the common resistance connected between 1 and 2 are 5. So minus 1 by 5. Resistance matrix is a symmetric matrix. We have to write in symmetric manner. And the last element is the self element, that is connected to second node. Second node self elements are 5 and 2. So 1 by 5. So plus 1 by 2. Which is equal to voltage V1. The voltage across first node is V1 and the voltage across second node is V2. Voltage at first node is V1 and the voltage at second node is V2. Which is equal to, here in the first node the current is entering, right? The current is entering. So it is positive 2. In the second node the current is leaving, right? The current is leaving. 4 amps is leaving here. And the 2 amps is also leaving here. So 4 plus 2 minus 6. In this node, apply a KCL. The current leaving are 4 and 2. So 4 plus 2 is equal to minus 6. Here the current entering is 2. So it is positive 2. We have to find the value of the current I. I can be represented by the voltage across this is V and it is grounded. V1 minus 0. I is equal to V1 minus 0 divided by 10 ohms. That is V1 minus 0 divided by 10 ohms. You need the value of V1, right? To know the value of the V1 can be found by using a Cramer's rule. If you want to find the value of the V1, you have to replace this first column with respect to the current column and expand that. You will get the value of V1 divided by the normal symmetric resistance matrix expansion, right? So, del is a normal symmetric resistance matrix, that is 0.30. After doing some mathematical calculation, you get 0.30. This 1 by 5 is minus 0.2 and this minus 0.2, and here you will get the value as 0.70, right? Del 11 is replacing that first column by the current value, 2 minus 6 minus 2 and 0.70. If you divide this by this, that is V1 is equal to del 11 divided by del R, right? Expand this, multiplied and minus. So 0.14 minus of minus, so 0.12, right? You will get here as 0.21 minus of minus, so 0.04. After doing this, we will get the value of V1 as 1.18. 1.18. Your I value across 10 ohms resistor is V1 divided by 10. Your V1 value is 1.18 divided by 10. You will get the value as 0.118 ampere. Your I value, the current flowing through the 10 ohms resistor is 0.118 ampere. Simple. Just by using the nodal voltage method, by using a Cramer's rule, it is very easy to find. I hope you understood the concept of this Cramer's rule applied in this nodal voltage method. If you have any doubt, please leave it in the comment section. And if you like the video, please like, share and subscribe to WiFi Learn. Thanks for watching the video.